everyone. Hopefully my mic is working. I can't hear much. Good evening, everyone. So just a few housekeeping things to start with. Please can I ask that you keep your phones on silent. We're not expecting a fire alarm, so if it does go off, please leave the building in an orderly fashion. Follow the instructions of the event stewards and make your way back to the car park. If you would like to tweet about tonight's lecture, please use the hashtag InsightsNCL. And following the lecture, there will be an opportunity to ask questions, and we'll have roving microphones. So if you could just put your hand up, and we'll get a microphone to you. So that just leaves me to introduce our speaker for this evening. So Dr. Jess Wade is a Royal Society University Research Fellow and lecturer in functional materials at Imperial College London. Her research focuses on materials for optoelectronic devices, with a focus on chiral organic semiconductors and how to optimize these such that they can absorb and emit circularly polarized light. For her PhD, Jess concentrated on new materials for photovoltaics and the development of advanced characterization techniques. And outside of the lab, Jess is very well known for a variety of different science, communication, and engagement activities, including writing this children's book, which I believe is available to purchase outside, and Jess is also happy to sign at the end of the lecture. So without further ado, I'll hand over to Jess.
Thank you. That's very embarrassing, and I promise I didn't ask them to sell the book. But it is a really, really sweet book, and I'll tell you a little bit about it. So yeah, my name's Jess. I'm a research fellow at Imperial, and I thought today I'd tell you a little bit about the science I do and also why I care so much about science communication and telling the stories, particularly of scientists from historically excluded groups. But I'm really happy to be in Newcastle. Newcastle is a really incredible place for science. My mum grew up here, and actually it was really a kind of founding place across the UK for teaching young women science. This is actually taken from a really beautiful book called A Chemical Passion, which is about teaching science, teaching chemistry particularly in girls' schools in the early 1900s. And this was in Newcastle Central High, which is just around the corner. But it was really groundbreaking in how it brought young women into chemistry labs for the first time. At the time, boys were learning Greek and Latin. That was very trendy and important, and girls were all learning quite hardcore physical chemistry. They were actually put on horses and carts and taken to Gateshead to do all of their labs in these big industrial labs, and then given milk and buns and sent back to Newcastle Central High. But I just think this is incredible. So they were really pioneers, Newcastle, in teaching young women science. After that, there's been some really phenomenal women engineers from Newcastle. Rachel Parsons was from Newcastle and went on to be one of the founding members of the Women's Engineering Society. Anne Macmillan, who was also from Newcastle, was a member. She actually was in the Women's Auxiliary Air Force during World War II, and then was the director of the Electrical Association for Women, which was really pioneering in how they taught women electronics and engineering. And actually, they tried to do it in these subtle and sleuthy ways, which speaks to how I'd like to tell the world about women scientists, and I'll get to that shortly. But they taught women through tea towels. They made these really beautiful tea towels that introduced women to how plugs worked, how fuses operated, and how you could use electronics to make your domestic life easier, which was really pioneering at the time, because they were trying to communicate with people in a platform they didn't have, and they found this mechanism to do it, which I still think is quite beautiful and relevant today. So Newcastle was then absolutely fantastic, and is still fantastic. My mum, this is a picture of my mum in the 1960s. This is a picture of her friend, who's still her friend, called Hillary, and they were out doing some good somewhere. I tried to find another picture, but I like this one because it just starts the article, whatever it was about them, saying, "Two Newcastle girls." That was to prove to you she was from Newcastle. And then so many fantastic people. Chia Nura, who's the Labour MP for Newcastle and was Shadow Minister for Science, Research and Digital, is probably someone that lots of you recognise. But I think she's a really phenomenal beacon for science and engineering, and really, truly one of the MPs that we can really be proud of. Every time she talks, I think she talks such sense on bringing scientists and engineering communities together. And then now you have the fantastic Juna Sathan at Northumbria University. Juna used to be at Imperial, where I work, and she's not only an associate professor for physics, but she's also, in her spare time, the Labour councillor for Newcastle. So there's some really phenomenal things happening contemporarily at Newcastle, and also historically, which make it a huge, huge pleasure and privilege to be here. So I thought I'd tell you a little bit about my story, my journey. That will be one slide, I promise, and then a little bit about the science I do, why I think it's so important that we do science at all, and then the kind of work I've done to try and tell the stories of women scientists. This is my, I'm not making an overview slide, so I thought I'd do it entirely with emojis. And they looked a lot smaller on my laptop than they do up there. So I grew up in London. I grew up in North London. I did kind of maths, physics, chemistry, and art at A-level. And then I went to art school for a year, so I did a year of history of art and Italian. I actually lived in Italy for the last few months of that year and really got this kind of overwhelming sense of how important the Renaissance was and how important interdisciplinary skills were. You know, at the time that Renaissance art was taking place, people were architects, they were metal workers, they were woodworkers, they could paint beautiful frescoes. They had this really insane insight into materials and structures and patterns, and they were allowed to be these kind of jack of all trades. They were allowed to do so many different disciplines. And I think one of the biggest challenges with education today, alongside the huge lack of physics teachers, is the fact that we don't let young people study physics and art and maths and chemistry and bring them all together. You know, we make people specialize so early that you can lose these hugely important creative parts of what you're passionate about. And certainly doing an arts degree and then going to work in this beautifully, wonderfully aesthetic physics department at Imperial, everyone always found that quite weird. You know, everyone I speak to finds it quite a bizarre thing to have done, but it feels quite natural that not only do we have to think about designing experiments and doing science that no one's ever done, and that obviously requires creativity, but also communicating science. And the processes, the things that we're talking about, the systems that we work with, you can't easily visualize them. You can't take a photograph of them. So you have to be able to illustrate them in some way. And actually having a training in the arts, I think, is quite useful for that. So I believe passionately in uniting whatever things make you come alive, and whether that's art and science or music and science, to keep it going. So I got to physics at Imperial. I ended up doing my PhD, as Greg said, in materials for solar. I then had a kind of, what will I do next? I really didn't know. I had no idea if I'd stay in scientific research, but I ended up having a really great viva. So the exam that you have at the end of your PhD was with two chemists, and then I strayed into this dark side of chemistry and actually joined the chemistry department at Imperial before starting a fellowship and a lectureship in materials. So I've moved between buildings, but not quite managed to leave Imperial yet. So I work on these really beautiful materials, these organic semiconductors, carbon-based semiconductors, as Greg mentioned in the introduction. And I thought I'd tell you a little bit about why they're so awesome. They are carbon-based or organic materials. They are the O in OLED, if you've ever wondered what that stands for. That's an organic light-emitting diode. They're the screens of, unsurprisingly, fancy screens that say OLED, contain OLEDs. Also Nintendo Switches, Apple iPhones, and Samsung Galaxies all have these type of materials in. And what's really interesting about them as a kind of material story is they were really a UK innovation. It was actually a bunch of academics at Cambridge that first saw organic materials could emit light if you drove charge into them. And then after that made a company, and that company got really, really good at making these organic light-emitting materials, started this whole research community in the UK that lots and lots of us now still work in. And then the company got sold to a big Japanese company, so we're no longer the big display manufacturers, unsurprisingly, in the UK. But it's a real story of kind of beautiful material science and accidental discovery that made this possible. I thought also I'd try and tell you a little bit about chirality. Chirality is this really interesting property of symmetry and shape that certainly the chemists or people who are doing chemistry A-level in the audience will have heard of. And I'll tell you a little bit about chirality and then how we can use that to control the spin of photons and also electrons. So carbon-based semiconductors, unsurprisingly, have carbon in. Carbon's an interesting element because it has these 6 electrons, 4 on the outside, and it can join up in all of these different weird and wonderful ways just with other carbons. So you can get all of these beautiful different structures, from things like diamond to graphite and pencil lead to these balls that are called fullerenes, and we use them a lot in solar cells, or something like these sheets of carbons, which form something called graphene, and if you roll up that sheet, you get these beautiful carbon nanotubes. And it was actually an incredible woman, who I'm hoping you've all heard of, but you may not have heard of, called Millie Dresselhaus, commonly known as Carbon Queen, who defined all of those structures. So actually, Millie Dresselhaus, long before we were able to synthesize or separate these carbon allotropes, was the one who described them all. She's also got this really fascinating story as a scientist. She moved, her family were Polish immigrants to New York, and she grew up in the Bronx with very, very little money, was absolutely desperate to be able to study science, knew from very early on she wanted to study science, so got a scholarship, a music scholarship, to attend a school that would let her do that. Ended up being fiercely successful. Enrico Fermi was her supervisor, so of nuclear reactor fame. She went on to win pretty much every medal you can win in nanoscience and materials. She was the first woman institute professor at MIT. She ran pretty much and led pretty much everything. She only died relatively recently, but this biography of her is by a fantastic researcher called Maya Weinstock, who's actually the science librarian at MIT. But it's just a really beautiful telling of a really fascinating story of someone who's given the world so much, and we really should know about and speak about more. I definitely included her in all of the lectures that I got to do. So carbon, super interesting element. The way that I'm interested in it, or the way that we think about it in these organic semiconductors, is when you've got this structure, and some of you will remember this as being something called benzene, but when you have this alternating system of single double bonds, because this system, and here it is when you've got 5 benzenes together. I actually put this because I thought Juna might be here, and Juna works on this molecule a lot, so I thought that might make her happy. This is called pentacene, because you have 5 of them. This makes carbon go from being something that's more like a plastic, an insulator, to something like a semiconductor. So just a quick recap of physics. When you have a metal, you've got absolutely no band gap between your conduction and your bonding bands, so this thing is a really good conductor. When you've got an insulator, there's a massive gap, and it's very hard for a material to conduct electricity. But when you have a semiconductor, like these materials that we work with, you've got a gap between your conduction and your bonding band, and actually this gap, you can move charges between by optically exciting it, so shining light on it. You can move electrons up to a different band, or you can force them to emit light, and those electrons would jump down and then emit light that way. So this band gap is really important for devices where you might want to turn it on and off, and where you might want to emit light if you're something like an LED, or where you might want to use it like a solar panel. So semiconductors are crucial to so many different technologies that we rely on today. When your friends in chemistry, when you're a physicist doing this or a material scientist doing this, you just tell people what to make. and then they go and try and make it for a few years. And then you're like, oh no, we've changed our mind and we want a tiny different structure. No, really, it's a lot more informed than that. And you try and use computers a little bit to help. But when your chemistry friends eventually do make these materials, they start life a little bit like a powder. So depending on how precious the material is or how long it's taken them to make, there may be very little of this powder. And then you can take it to the lab, you can dissolve them lots of the time, and you can make these beautiful semiconducting inks that we can then print onto different surfaces. So you take this powder of these interesting semiconducting molecules, you have this huge versatility in the chemistry of them, so you can change what color they absorb or color they emit, how they transport electrons, whether they can move around ions, and then you can print them with these low-cost printing techniques. So you have a semiconducting ink now that you can print onto something like a flexible surface. And this just gives you absolutely huge space to be innovative and to design. So you go from being able to make kind of fully flexible solar panels to really clever solar panels, and this diagram maybe doesn't convey quite how clever they are, but solar panels that transmit visible light, so say this yellow line is visible light, and then absorb in the ultraviolet and infrared. So using these clever materials, you can make things that absorb in the UV and the IR, so they generate electricity from parts of light we can't see, but let through light that we can see. So you can coat windows in these types of materials and kind of have almost continuous power generation from them. I've already told you that they're absolutely fantastic in display technologies, so in things like iPhones and also these beautiful Nintendo Switches, and then also in bioelectronics and measurement, kind of human health monitoring. So being able to print circuitry that can monitor for different disease or biomarkers, and even different diagnostic techniques that you can implant into the human brain. So you have this absolutely huge space for innovation. I'll come back to tell you about some more other fantastic people in a bit if I have time. Now to tell you a bit about chirality, and the story of chirality is kind of absolutely fascinating. Chiral objects exist as a pair of non-superimposable mirror images, which is why I keep putting this picture of hands up. I'm very aware that there's a chemistry professor who works a lot on chirality in the audience, so I'll have to get my definition right as a physicist. But your hands are perfect pairs. Your hands are perfect chiral objects. If you put them together palm to palm, then they're mirror images of one another. But if you put one on top of the other, then there's no way you can rotate that hand on the top of you to be able to be a mirror image of the one on the bottom. And that's what that kind of fancy word of non-superimposable means. But we see it a lot in the naturally occurring world. And actually, it was Louis Pasteur who was the first person to discover chirality at all, or to measure chirality. So long before he gave us pasteurization or all of the work that he did on vaccines, Louis Pasteur was kind of in his early 20s. He didn't quite know where to go in life, and he was actually an art student. And he was looking in barrels of wine. And in these barrels of wine, he found these beautiful crystals of something called tartaric acid. And these crystals of tartaric acid would form. And Louis Pasteur noticed that if he shone light through these crystals, particularly light that was plane polarized, so linearly polarized light where the wave is all oscillating in one plane, if he shone that through these crystals of tartaric acid, it would rotate the plane of polarization. So you had this optical rotation going on when he shone light through these crystals. And actually, that was because he'd discovered that tartaric acid had these left and right-handed chiral forms. And what he showed was if you shone it through a mixture that had 50% left-handed and 50% right-handed forms, you didn't have any of that rotation happening. But if you shone it through crystals that were just one-handedness, you'd have the rotation happening one way or the other. And there's really beautiful kind of literature discussing how he was able to make this big leap. No other scientists at the time had been able to do it. And here's a 20-year-old, he hadn't even submitted his PhD yet when he first discovered this. And actually, it was because he was trained in a particular type of art. Pasteur did something called lithography, where you etch away an image and then press something down on top to create a mirror image form of that image. So some say, I mean, it's a stretch to say that's definitely why. But some say that that actually contributed him to him being able to discover this. So his training in the art made this possible. Training in the arts made this possible. I thought I'd try and show you what optical rotation looks like. This is a really beautiful demo that we got for one of the science festivals at Imperial. So at the back here, one of these big circles with numbers on the edge is a linear polarizer. And on the front is another linear polarizer. So they're things that will let us just look at this rotation. So we're just trying to look at those. It's kind of like we've constrained the light to that one plane. And in the middle, this colorful thing is a whole bunch of sellotape, particularly sellotape that's made of cellulose, because that's chiral. So if you put this chiral tape in between these two linear polarizers, you get really, really beautiful effects. And I'll just show you. Look at how cool it is when you rotate it around. So every single color of light rotates by a slightly different amount. So you get these really, really beautiful patterns forming because of that optical rotation, which I just think is absolutely fantastic. Yeah, it keeps turning around, Jess. Let's see. So chirality is interesting because it exists across multiple length scales. So we see chirality at the subatomic scale in things like electrons and photons. So electrons spin up and spin down a chiral. Light can be twisted clockwise or anti-clockwise, left or right-handed, and that's chiral. We see chirality at the molecular scale, so in molecules that can be shaped to be like springs. So here's that benzene structure I showed you before, but you can see that the way that the benzenes are connected together in this molecular shape means that that molecule can't sit flat. It's very different to that rigid molecule I showed you before. This is coiling up or springing down like a spring. So you have these spring-like molecules, which are a slightly different length scale to those electrons and photons. We also see chirality in lots of biomolecular systems, so things like DNA or proteins, they're also chiral. And actually in lots of macroscopic objects, in lots of the naturally occurring worlds. So if you look at things like shells, actually snail shells or lots of fossils, they always twist. Actually, majority twist in one direction. In things we make, things like fusilli pasta has a twist. In the barks of lots of plants, you see this twisted structure. And actually, even in the arms of these spiral galaxies, you have that clockwise twist. And actually, even the light that comes to you from these galaxies or in the gravitational waves that come to you when you measure and detect gravitational waves from black holes colliding, do you see this chirality? And something that's really interesting about life, naturally occurring life on planet Earth, is it's selected for particular chiralities. So we've got a left-handed molecule and a right-handed molecule here, and I've tried to show with a little same clockwise spring exactly what you have. But DNA is always right-handed, so if you look in the DNA of all naturally occurring life on planet Earth, in me, in a plant, in some kind of sugar that you might look at, you'd always, not sugar would be also right-handed, but you'd always see this right-handed DNA. And if you had something like a protein, you'd always see it as being left-handed. The other interesting things that have one-handedness, if you look at shells, they're always right-handed. It's incredibly hard to find a left-handed snail, for example, if you go out and try and look for one on your way home. Interestingly, pasta is also always right-handed, and that might be because it's easier to buy one type of machine that everyone always buys. But even if you look at things like the barks of plants, depending on where they're from, if they're from China or Japan, you have this twist in different directions. So life on Earth has really selected for particular handednesses, and we're not entirely sure why that is, but it seems to be a design rule that makes processes more efficient. So how are we thinking about using it in technologies? And this will be my kind of one main example of this. What we're thinking about using it in is particularly in displays, and we're thinking about doing that because the way that we construct displays is by assembling them out of lots of different pixels. So if you look closely at the display of an iPhone, you have these blue, green, and red pixels. And if you took a vertical section through one of those pixels look like, you'd see all of these different layers. So we have a whole bunch of different layers. Either side of these stacks, we have electrodes, then we have some optics, we have layers to make it easier to inject electricity, and then we have the actual material that's going to emit light, whether that's red lights, green lights, or blue lights. And what happens is we inject electricity from either side of these. Those charges will move through these layers, meet somewhere in the middle of this active layer, and then that will emit light. And what we put into this sandwich-like structure is this anti-glare filter. And this anti-glare filter is really important because it means if you're outside trying to send a text message on a sunny day, or if you're standing with a bright light from behind you, you can still see the image that you get on your screen. And that works by taking unpolarized light, so light that doesn't have a handedness, turning it into circularly polarized light. That then moves through this sandwich structure, hits off this electrode at the back, which is shiny, it's like a mirror, inverts the handedness of that light, and that then tries to get out and get back through that anti-glare filter and then gets stuck. So the anti-glare filter turns the light into twisted light, it propagates up through your device, hits that mirror, inverts handedness, and then can't get out at the bottom. And that's great, and it works, and it's what's currently in your technology at the moment. But it means that if the pixels in your phone are emitting unpolarized light, which is half left-handed and half right-handed light, then only half of that light is getting out of your display. So despite you powering it as much as you can, and despite those pixels being as efficient as they could be, half of the light is getting blocked in that anti-glare filter. And whilst you can get around that by turning down your brightness, when you have things like 5G, which are very power demanding, you've got to think more creatively about ways that you could generate a little bit of an extra boost of brightness. So what you can do is turn that light into circularly polarized light, and if that light's circularly polarized light of one-handedness, it could move through that anti-glare filter and then absolutely boost your brightness. And it's kind of interesting scientific challenge to think about how you might do that. So what can we learn from to try and generate this circularly polarized light? And there's actually a few systems in nature that are pretty good at making or reflecting circularly polarized light, making, reflecting, or detecting circularly polarized lights. There are these absolutely beautiful beetles called jewel beetles, and these beetles have a really interesting structure in their shell so that it's like this kind of twisted stack. Every single layer in the beetle shell, it's made from a biopolymer called chitin, and every single layer in this shell is twisted a little bit with respect to the layer below. And that means if you look at light that reflects from the beetle's shell, it comes back to you twisted. And actually you can see it if you look through 3D cinema glasses. So if you look through one lens, you'll see it brilliant color, and if you look through the other lens, you don't see any color at all. And I've got that in this beautiful little video that I made earlier. but there's through one lens, no color, the other lens, beautiful color. It's really mind-blowing. And actually, if you didn't believe me about that thing of looking at these beautiful beetles, of circularly polarized light reflecting in a mirror, I put a little video on now, and you can kind of see it. So this is the beetle, and then there's a mirror behind, and you can see the two different colors of left-handed light hitting the mirror and becoming right-handed light through. I find that absolutely incredible. So we can learn a lot from the beetles about this structure and how you can generate circularly polarized lights. Actually, other naturally occurring species, these beautiful mantis shrimps have evolved to be able to reflect circularly polarized light. In this kind of contrast image below, parts of the mantis shrimp shell reflect circularly polarized light. And they've actually got incredibly clever components in the rods and cones in their eyes that can detect circularly polarized light. So this is one of those common cases in trying to be innovative in materials or engineering where nature's been doing it really well for a really long time. And we can look at these structures and learn from it and think about how we can better inform the design of what we're working on. But what we're getting really good at, and what people here at Newcastle and then also across the UK are thinking about, is how can we make better screens like this, and do that by using these beautiful molecular systems. So how can we boost how twisted that light is by thinking carefully about the material science? And it takes a lot of optimization, so it takes a lot of playing around in the lab and doing exciting experiments, going to do experiments sometimes in different countries. I've put the highlight of my thoughts of each of these experiments in the text, but we get to play with really big magnets, we get to play with beams of ions, very powerful lasers. I liked it so much, I made the laser LA white so you could still read it, and then beams of electrons to really try and work out what's going on. So it's not just a case of looking at what the molecule looks like in a drawing and then putting it on a surface and trying to work it out. These things are really, really tricky to optimize. So you spend a long, long time trying to think about how to make that packing structure more efficient, or how to optimize the mixtures that you've got or the way that you've processed it so you can get more of that twisted light out. And it is absolutely the most kind of incredible job and amazing space to work in if you want to be innovative. So the kind of big so what about the science that I've just shown you, before I talk to you about everything else, is that in 13 minutes, is that chirality is obviously shown in biological system and the natural world as being a massively important design rule. If we can use it to control the twist of light and the twist of electrons, can we use it to design more efficient technologies for tomorrow? So whether that's in optical or electronic devices or quantum technologies or different kinds of semiconductor devices, can chirality be this design tool that will be really useful for making that more efficient or more functional? But I thought I'd go a little bit bigger picture and talk about why study science at all. Why is it important that we do this, or why is it important that we get a new generation of scientists to come in and do this? I think the opportunities for absolutely massive breakthroughs is really incredible. So I put a picture here of one of the quantum computers. I think this is IBM's quantum computer. The UK has just put a massive amount of money into their quantum technology program, £2.5 billion over the next 10 years. For quantum computers and quantum sensing systems. The people who are really innovative in this space will be in school right now and starting to think about doing physics right now. They'll be the ones who go out and deliver on these different kinds of technologies. Being more innovative in the materials, being more innovative in the engineering, and making it possible to realize these things. Making breakthroughs in medical imaging, making breakthroughs in vaccine design, all of this needs a whole new generation of scientists who are more creative and more interdisciplinary and more willing to work with scientists from different backgrounds. We also have these kind of immense global challenges, all of which require a science or an engineering solution, whether that's kind of growing numbers of floods or wildfires, or just getting people to think more creatively about the energy systems that they use. We really desperately need scientists there. We also need scientists to help government understand science. When I was trying to think of a picture to convey this, I found this quite funny picture of Rishi Sunak. And if you look closely, he's looking at a printed structure of a molecule, and it's nicotine. Why did he print this? But anyway, last year was a really interesting time, because for the first time in history, they set up this Department for Science, Innovation and Technology in the government, which means we now have a minister to represent science who's in all cabinet meetings. So if you are thinking, I'm quite interested in policy, I'd quite like to influence what gets funded when these national semiconductor strategies or national quantum strategies comes out, whose voice is being heard, who's driving which directions the UK goes in. I think that's a really exciting time to be in that space. We desperately need more scientists who are able to communicate with policymakers, who understand the global field and can influence what happens. So you could study science for breakthroughs. You could study science to solve climate change. You could study it to help out with policy. You can go into broadcasting. I was looking up all of the people who are the science representatives for Radio 4 or the science writers for The Guardian, and pretty much all of them have physics or chemistry degrees. So it's a really hot place if you wanted to go into journalism or to broadcasting. You could start a company. You can make things more fair and equitable. I couldn't quite think of a picture to represent these, despite racking my brains hard enough. Or I guess what most physicists do is go into the city or into patent law, but I put those last because I think they're the most boring ones. So you can do all of these absolutely remarkable things by thinking about science. And it's one of those opportunities I think is just really important that we try and get everyone to realize the space is absolutely infinite. If you have an idea as a scientist in the shower the night before, you can go in the next day and make that experiment possible and know for a few moments something that no one in the world knows. And I think that's just such a huge privilege. Everyone should have that opportunity. So I spend a lot of my time, I've always spent a lot of my time trying to think about ways that we can take science and make science more engaging for young people, and particularly recently for teachers. I put these photos up just from, this was the first massive event I organized for young women scientists actually at Imperial. It was in just the final year of my PhD, about 2016, and it was 250 young girls who came into Imperial. I don't think there's ever been that many young women in the physics department at Imperial of my entire life. And I organized the whole thing without my PhD supervisor knowing, which is quite a hard feat. And it was absolutely incredible. It was kind of this stream of different science experiences and workshops that they did. And the most amazing thing about doing this is they're now undergrads. You know, I now meet them and they're kind of undergrads or engineering students who've gone on and taken that day. But since then, I've done a whole bunch of stuff and thought a little bit more about how we can do it better. So I think maybe lots of people here do a lot of science outreach or working with schools. And I think really what I've learned desperately is how much teachers need to be involved with it. I actually the reason I put this up is because I went last Saturday to speak to something like 150 physics trainee teachers in Kent. They desperately want to hear more stories of science or how to make their science curriculums more inspiring and engaging for young people. And of course, you can go out and speak to young people individually and personally and one-on-one. But teachers have this huge multiplier effect. And actually, if we can get teachers to be excited and enthusiastic about science, often in subjects like physics, they're teaching physics without a degree in physics, maybe even without an A-level in physics. So they really need a hand to make it more engaging and more exciting. So I think if for one thing, I'd recommend if anyone in here does outreach with young people is think about inviting teachers or parents in, make the content that you're doing relevant to a curriculum, and try really hard to make the science kind of contemporarily relevant and tell the stories of scientists as well. Something that I did recently that I'm really proud of was this cool workshop that we created on AI. So we're trying to get young people, this is in our new campus in White City, which is in a really interesting part of London, and we run like a family science club there on Saturdays. And we wanted to get young people and their parents to think about what AI meant for them and their futures. So we made this workshop on AI and art, and it starts with all the parents, all the families coming in, and we make like a little art gallery where we have art that's by robots or art that's by humans on all of the walls, and they have to go around and decide whether they think it's by a robot or whether they think it's by a human. And it's kind of Kandinsky and really left field Picasso, so it's art that looks a lot like it could be by robots. And it's such an interesting discussion. And then we talk about AI being able to make art, and then they make robots, and they make art with the robots, and then talk about who really made the art, whether they made it or the robot made it. So trying to think in a really left field way about introducing these topics to them. And we did this workshop first about this time last year, and at the time, none of the families had heard of ChatGPT or anything like that. And we did it again about a month ago, and everyone had heard of it, and everyone was using it all the time. So just getting people to be aware of technology that's coming in and will be a huge part of their life, and kind of giving them the ownership and empowering them to be the ones who think about how to do it, has been a huge part of what I think about science outreach and communication. So as Greg mentioned, I've had the opportunity to write this really beautiful book. So Walker, the kids' book publisher, wrote to me in about 2017 and said, have you thought about writing a book? And of course, I'd never thought about writing a book, but I went and had a chat with them. And for everyone who deals with academic publishing, when you're a scientist and you try and publish a paper, it's this kind of horrible process where you write your paper and then you send it off, and then a bunch of anonymous people are like, no, it's rubbish. And then you have to defend your ideas to these anonymous people. But when you go to children's book publishing, it's just so wonderful and lovely. And everything you say, they're like, oh my gosh, like no one's ever said anything as creative or as innovative before. And so I went to speak to them about what we could do to make people excited about materials. And after about a year, we came up with this idea of writing this book about nanomaterials and science and how we do it. And actually, the real tour de force, the wonder in this is Melissa Castrion, the illustrator. She's just so beautiful. The books, the way that she visualizes things and tells stories. So it's a kind of storybook and a picture book about science and about material structures and patterns. But actually, as a tool for outreach, it's been incredible. So we've done loads of workshops together with schools where Mel draws with a visualizer, just like this. She draws on a table like this, oh gosh, all of these different structures, and then I talk about them and how that impacts their properties, and then all the young people in the audience draw them too. So you have young people drawing incredibly complex crystal structures, and it's really funny. These crystals are called perovskites, but Mel can't pronounce that because she's an artist, so she calls them perovskites, and it's just the most sweet thing. But anyway, you have this real opportunity to get people who are otherwise artistic and creative to be enthusiastic about material science. And we also made a great workshop around carbon nanotubes and making them. So thinking again, how can we communicate the science that we do in this really beautiful and visual way? But I wanted to briefly tell you a little bit about this project that I've had for the last few years on trying to tell the stories better of women scientists. This was from 2020. So this was a report that The Independent covered, but saying out of all of the GCSE science curriculum, so what young people learn up to the age of 16, it's not mandatory to learn a single woman's name, a single woman scientist's name. My friend actually went a little bit further, my friend Claire, and looked at chemistry textbooks in the UK and Ireland. And she went through all of the images and the named people in these chemistry textbooks. And she found that women were only in them if they were demonstrating dyeing your hair or painting your nails. And they never had a name. Even in Irish textbooks, they didn't have the name of really notable Irish women scientists like Kathleen Lonsdale. So this thing kind of horrifies me. You know, it makes me so angry because there's so many phenomenal women scientists who we're just not talking about. In 2017, another great thing happened. This amazing film came out called Hidden Figures, which told the story of the African-American computers, the mathematicians at NASA, who enabled human spaceflight. So huge time when all of this kind of reckoning was happening. And then the US Department of State decided to put together this international visitor leadership program themed around Hidden Figures, where they took 50 women scientists from 50 countries around America for about a month. And I was the UK scientist, and there was 49 incredible women from Mongolia and Vietnam and China and Nigeria. And I felt so boring because they were all so inspiring and so incredible. But they were, you know, incredibly eminent, incredibly doing huge things in research, huge things in industry, professors, really senior research scientists. And every single one I met, I'd Google them, and every single one wasn't on Wikipedia. So I'd look them up, and their biography wouldn't be on this incredibly important encyclopedic platform. And then we'd go to these universities. We went to universities in DC. I've been to such obscure places in America because of this trip. Nebraska, Ohio, obscure places in Florida. And we'd meet all of these amazing women, and I'd look them up, and they wouldn't be on Wikipedia. And I guess it just kind of frustrated me. It frustrated me because Wikipedia is this hugely important educational platform. You know, from a perspective of democratizing access to knowledge, everyone in the world gets on it. Everyone in the world uses it, whether they're kind of a child, a high school student, a university student, an academic, a lawyer, a journalist, a doctor, a professor. All different walks of life use Wikipedia. No matter what their political leaning is. So if you're very right-wing or very left-wing, people use it. It crosses that partisan divide in a way that most media doesn't. So Wikipedia is phenomenally important, and yet we're really not doing a good job of telling women's stories on Wikipedia. So this kind of combination of events, learning that we weren't talking enough about women scientists or teaching enough about women scientists, learning again that Wikipedia was this hugely important resource, really motivated me to do something about it. So at the beginning of 2018, I started writing these Wikipedia pages every single day of women scientists and engineers from historically excluded groups. I started just with women physicists, but then I finished all the women UK physics professors pretty quickly. So I had to go broader. So I've been doing this for a really long time of kind of researching and writing these biographies of psychologists and neuroscientists and chemists and all of these different, completely different disciplines. And I guess it's been this huge privilege for me. You know, I get home at night and I just sit down with my laptop and I learn about a whole new field or a whole new technique or a whole new journey that someone's had for science. So I learn so much, and it's so inspiring and so exciting that all the time I feel like I should be doing that. I really wish I was in that field now. You know, exactly what they do is so incredible. But just the people that you write about are so amazing. So I've written about 2,100 pages by this point. Just to give you a sense of the types of people who aren't on Wikipedia, who are now on Wikipedia, Sarah Gilbert was the vaccine designer at Oxford who gave us the Oxford AstraZeneca vaccine. At the beginning of the pandemic, I was determined that all women epidemiologists and public health doctors would be on Wikipedia so that journalists could contact them instead of just profiling men in the news. And actually by the end, no, I think it has ended now. But by the end of it, they were all the ones who are on the news all the time, all of these amazing women I'd written about. So I really felt it was incredible. Actually, yesterday I had a call with a Radio 4 producer of some medicine show on Radio 4. And she was trying to look for people for Series 2. And she listed every woman they'd had on Series 1, and I'd written every single one of their Wikipedia pages. So I was like, well, this is a massive success for me. But Sarah Gilbert, her Wikipedia page at the beginning of the pandemic was, Sarah Gilbert is a professor at Oxford. And that was all the sum total of knowledge about her on Wikipedia. And obviously, she's made it now because she's a Barbie. Kizzy Corbett was the vaccine designer at Moderna. She made the Moderna NIH vaccine, one of the mRNA-based vaccines. She's now one of the youngest ever full professors at Harvard. She's a phenomenal woman. And after I put her Wikipedia page up, Fauci nominated her as Time Person of the Year. And I just really love the idea that Fauci sat there and read her Wikipedia page. Not that he wrote the nomination, but I think that's fantastic. But the most amazing Wikipedia biography story that I've ever worked on was this amazing woman called Gladys West. She's born in 1930, so she's kind of 93, 94 now. She was born in Virginia. She went to a historically black college and university and did maths, and then she ended up working in a high school for a little bit before working for the Navy to do the kind of groundwork for GPS. So she described how non-spherical planet Earth was so that you could put satellites in orbit around planet Earth and be able to do things like Google Maps and Apple Maps and satellite navigation. So none of that would be possible without Gladys West. But when I learned about her in February 2018, there was like about a 7-second video about her on a CIA website, and then absolutely nothing in a kind of collected history way. So I pulled together all of these different biographies. She's very active in her community, so I found a lot through there. And the kind of beautiful thing about Wikipedia is I put up this page at 11 p.m. UK time, and then someone in California will add to it or translate it or add parts that they can find. So nothing's ever kind of static. You print an encyclopedia and it's out of date as soon as it's printed. This keeps growing, it keeps moving, it keeps evolving. So Gladys West, I knew I was onto this beautiful story. Then a few months after I put her Wikipedia page up, the BBC put her in their top 100 women. So if someone's named on the BBC website, their Wikipedia page really pops off. She was getting like 2,000 views an hour on her Wikipedia page. So I was just, ecstatic. Everyone in the world was reading about her. And then the US Air Force inducted her to their Hall of Fame, and she was 89. So then you get all these photographs of her, which have the right license to be shared freely online. So we could put them on her Wikipedia page, which was fantastic. And then The Guardian wrote a great profile of her as the hidden figure who helped to invent GPS. And again, they must have looked at her Wikipedia page to write this, so win-win. And then the coolest thing, in 2021, the Royal Academy of Engineering, so our UK-based Royal Academy of Engineering, awarded Gladys West the Prince Philip Medal and Prize. And this had never before gone to a woman in the entire history of the prize. And the first person to win it, the first woman to win it, was, this 90-year-old mathematician from Virginia. I thought it was just the most beautiful thing. So whenever I teach people about how important it is to edit Wikipedia, or everyone always wants to learn how to edit Wikipedia, but really it's so easy to edit. Oh, I've cut it off here. But if you imagine going to a Wikipedia page, at the top there's a button that says read, and next to it says edit. And the sum total of learning how to edit Wikipedia is pressing that button that says edit. But anyway, I was telling some tech company how to edit Wikipedia, and they scheduled a Zoom with me for a few days later. And I thought it was just me and them, but it was actually a Zoom where they got me to meet Gladys West on the Zoom. So it was my ultimate fangirl experience. So I was so excited by it. I had to have, her niece was about here, just trying to moderate my enthusiasm, because I was like, she'd become such a celebrity in my eyes. And she actually said that now she was so famous, like every time there's a list of incredible mathematicians, people are saying Gladys West should be on that, we should add Gladys West's story. And she was saying that now all her grandchildren think she's this celebrity whenever she walks in the house. So it is just absolutely beautiful. So I could go on for ages and ages, and I was going to say a bunch more stuff, but I'll just end so that we can have some time for questions, by saying that I think being a scientist is really the coolest job in the world. And you get to do incredible things that you never thought was possible. This was in the State Department in DC. This is Caroline. She was the Swedish representative on this trip. And they said, you two cannot sit on that stage. And so we did. And then this was at a physics conference in Birmingham. And all the time at this physics conference, they said, oh, a Nobel laureate's coming. And I thought it would just be a really boring old man. So I was like, oh, that would be so boring. And then it was Malala. Malala came to our physics conference just to say hi, because she was across the road at school in Birmingham. This was with Donna Strickland last year, so another cool Nobel laureate that you get to meet at a physics conference. A few years ago, Google decided they wanted to make some kind of video about us. They turned me and my friends into a cartoon about scientists who work on cool materials. Wait for it, this is my ultimate claim to fame. Casio made a calculator with my face on it once. But I'm so embarrassed by this horrible drawing that I've never opened it, and it's actually just in a box in my bedroom somewhere, but I put it there now. And then you get to write children's books, which is really out there. I never really dreamt this. I could never have dreamt it would be possible. And actually, not only is it in English, but it's also in other languages, including Mandarin, which I just think is so neat. So yeah, I think it's a huge privilege to do science. I think we all have a responsibility to communicate the science we do. I think the world needs a new generation of scientists who are ready to do interdisciplinary things in a really creative manner. And we've really got to get better at telling the stories and celebrating women scientists and engineers to reflect what they're doing now, but also to inspire future generations of scientists. I put a few little books here that I can leave here when I take some questions, if you have any questions. But other than that, I just have to say thank you for inviting me. It's a huge honor.